We are in section 8.2, testing a claim about a proportion. Remember, the best point estimate of P, the proportion of the population with a certain characteristic, is given by P hat, which is equal to X over N, where X is the number of individuals in the sample with a certain characteristic, and N is our sample size, is approximately normal with a mean mu equals P and a standard deviation of P times 1 minus P divided by N, if the following requirements are satisfied. So first thing is the sample has to be a simple random sample. The second is that the conditions for the binomial distribution are satisfied, and N times P and N times Q are both greater than or equal to 5. And the test statistic for testing a claim about a proportion is Z equals P hat minus P divided by the square root of P times 1 minus P divided by N. Right below this, we have a box that says testing hypothesis regarding a population proportion p-value approach with a TI-83 or 84 calculator. So let's give that a star. Again, the steps that we need to check to make sure that we can actually perform the test are listed there. Determining the null and alternative hypotheses, you'll notice that's P equals P naught for all the nulls, and then our alternative hypothesis depends on if it's a two-tailed, left-tailed, or right-tailed test. Step 2 is figuring out alpha, again, which is usually given to you. Step 3 is find the p-value and the test statistic. If necessary, enter data into L1. So we're going to stats, test, 1 prop z test. P naught's the value of the population proportion in the null hypothesis. X is the number of successes, and N is the sample size. Next thing is selecting the direction for the alternative hypothesis. Highlight calculate, and you get a test statistic of Z and a P for p-value. Step 4 is if the p-value is less than alpha, we reject the null hypothesis. Step 5, we're going to state our conclusion. The next example says test the hypothesis using the p-value approach and assume that the criteria has been met. So this is pretty much just getting us used to the fact of using a calculator. So it is giving us the value of our null and all our alternative. So we'll just go ahead and rewrite those down, but this is normally something you would read the problem and have to figure out on your own. So our null is that the proportion is going to be equal to 0.6. Our alternative is going to be that the proportion is less than 0.6. We are going to go stat to test. And we're going to go to 1 prop z test. On 1 prop z test, we are going to enter in p naught, which is 0.6. X for this problem is equal to 75. And N is equal to 250. Our alternative hypothesis is a less than. And then go down to calculate, select enter, and you get your values there. You get your p-value, and Z, which is your test statistic. From the calculator, we get a p-value equal to 0. And this is less than alpha. Alpha was 0.05. So this means we are going to reject our H naught, or our null. We normally would write a conclusion. But since this is not really a word problem, I will leave that up to you to kind of try on your own. But we will do that from now on with the other word problems that we have. So on the next page, the example at the top says the drug Lipitor is meant to reduce total cholesterol and LDL cholesterol. In clinical trials, 19 out of 863 patients taking 10 milligrams of Lipitor daily complained of flu-like symptoms. Suppose that it is known that 1.9% of patients taking competing drugs complained of flu-like symptoms. Is there evidence to conclude that more than 1.9% of Lipitor users experience flu-like symptoms as a side effect at the alpha equals 0.01 level of significance? First thing we need to do is verify that we can actually perform this test. And in order to do that, we need to check those 4 things that were written in the box on the previous page. So first one, this is a simple random sample. Second is going to be we have to make sure that all the conditions for the binomial are satisfied. So that is that we have 863 trials, and they are independent. So those are two of the things. Next, we have that there has to be two disjoint outcomes, which there are. Flu-like symptoms or not. So two disjoint outcomes. And then the next thing would be that we have a fixed probability, which we do. The probability of having those flu-like symptoms is going to be 0.019. Then we have to check that n times p and n times q are both greater than or equal to 5. So n times p has to be greater than or equal to 5, and n times q has to be greater than or equal to 5. N is our sample, and our sample is 863 people. P, which is that 0.019. When we multiply this out, we get 16.4, which is greater than or equal to 5, so check. N times q, so 863 times q. Q is 1 minus p, which works out to being 0.981. When we work this out, we get 846, which is greater than or equal to 5, so check. So all of those conditions that we needed to have satisfied are satisfied, and therefore we can go ahead and do the test. In order to do this test, we need to read the problem again and write down our null and our alternative hypotheses. So H0 and H1. So the first question is, are we dealing with a means or a proportion? And this is clearly a proportion that we kind of said already. So I'm going to go ahead and put P's down for proportions and equal sign. That proportion is that flu-like symptom that we have, which is 0.019. And then as you read through the problem, it says we can conclude that more than, and that's our giveaway that our alternative is going to be greater than that 0.019. And again, using our calculator, one prop z test, we need to put all those numbers in. The numbers that we do have is n, which is our sample size, which is 863. We have p, which is our proportion that we have, which is our probability, 0.019. And x is the number of people that experience this, which is 19. We're going to go to stat, test, one prop z test. Our P naught for this problem is 0.019. Our X value that we have is 19. N, our sample size, is 863. Our alternative hypothesis is greater than. Go down to calculate, select enter, and again you get your Z, which is your test statistic. You get your p-value. So from the calculator, we get a p-value equal to 0.2582, which is greater than alpha, which is equal to 0.01. And this means we do not reject H0. So from here, we need to write a conclusion. So we can conclude that there is not sufficient evidence at the alpha equals 0.01 level of significance to conclude that more than 1.9% of Lipitor users experience flu-like symptoms. So looking at the next problem that we have, it says in 2000, 58% of females aged 15 years of age or older lived alone, according to the U.S. Census Bureau. A sociologist tests whether the percentage is different today by conducting a random sample of 500 females aged 15 years of age and older and finds that 285 are living alone. Is there sufficient evidence at the 0.1 level of significance to conclude that the proportion has changed since 2000? Assume testing criteria has been met. Now, since it says assume testing criteria has been met, that means that we do not need to verify that we can actually conduct this test. And so we can actually go in and start by writing our null and our alternative hypotheses since we are performing a test. Next thing is, do we have a what's our parameter that we have? Is it proportions? Is it means? Is it standard deviation? So for this problem, it's proportions. We're talking about the percentage of women that are living alone. And so I'm going to go ahead and put a P down. Equal sign for our null. And we are saying 58%. So I'll write that as a decimal, 0.58. And then it says, has it changed since 2000? So change should be not equal to 0.58. And that number stays the same. We're going to go stat test to 1prop z test. Our P naught is going to be 0.58. X is equal to 285. N is equal to 500. Our alternative hypotheses for this problem is not equal to. Go down to calculate, select enter. Again, you get your test statistic and your p-value. So from the calculator, we get a p-value equal to 0.6505, which is greater than alpha equals 0.1. And this means that we do not reject H naught. So in conclusion, we would say there is not sufficient evidence at the alpha equals 0.10 level of significance to conclude that the proportion of females living alone has changed since year 2000. So the next example that we have, I'm going to go ahead and circle that one, and we will go ahead and work that one out together in class. And we have another one on the next page. This question was posted on the America Online website. Do you believe that the Loch Ness Monster exists? Among 21,346 responses, 64% were yes. Use the 0.01 level of significance to test the claim that the majority of people believe that the Loch Ness Monster exists. Use a confidence interval approach and assume that all criteria for the test have been met. So we don't need to prove that we can actually go through with this test. We can just go ahead and jump right into it. So we can start with H naught and H1. So the first question we have is, what parameter are we talking about? We're talking about the percent of people that believe that the Loch Ness Monster exists, and that's a proportion. So I'll go ahead and put P. Our null again gets an equal sign. And then what number is it that we would put in here? Well, it's asking us to test the claim that a majority of people believe that the Loch Ness Monster exists. So what does a majority mean? A majority means more than 50%. So more than 50%. So our null would be the proportion is equal to 0.50, and more than would be greater than 0.50. So in order to do this, it does want us to use the confidence interval approach. So we will be using 1prop z int. But in order to get that set up, we need to think a little bit. First thing is we have n. And n is the number of people that responded, and we have 21,346. X is going to be equal to the 21,346, and we'll say times, and our value here that we'll put down is going to be that 64%, which is going to be 0.64. When we multiply this out, we get 13,661.44. And we need to round this to a whole number. So rounding this to a whole number, we get 13,661. That would be our value for X. Then we need to kind of look at what our confidence level would be. Remember, with confidence intervals, that was always the middle part of the problem that we're talking about. Since this is a right-tailed test, that means that alpha would be over here in the right tail. And alpha for us in this problem is equal to 0.01. And so that means that since we are dealing with a confidence interval, I need to also have another line over here that's going to be exactly the same value to make this a two-tailed test. And that's how that works for any confidence level that we would have. It's always that middle, that plus or minuses are the ends. And so the value that we would have in the middle, That's going to be 1 minus each of those n's, works out to be 0.98. So our C level on your calculator, confidence level, is going to be 0.98. On your calculator, you are going to go to Stat, Test, down to 1 prop z int, x is the value of 13,661, n is 21,346. Our confidence level on this problem is 0.98. And go down to calculate, and we get our interval with our lower bound and our upper bound. And the interval that we get is going to be, and I'll round 3 decimal places, it's going to be 0.632, comma, 0.648. And so we need to look and see if that original percent that we had, which was 64%, lies within that range that we have from our lower bound to our upper bound. And since our original percentage, which was 0.64, is in the confidence interval, this means that we do not reject H0. So from here, you can write a formal conclusion, and I'll leave that up to you guys to try on your own, and then we'll discuss that together in class. The next section is 8.3, which is testing a claim about a mean. It is very rare that we test a claim about an unknown value of a population mean mu, but we somehow know the value of the population standard deviation. When the standard deviation of the population is unknown, the test statistic has a distribution called the student t-distribution. The test statistic for testing a claim about a mean is x bar minus mu divided by s divided by the square root of n. The box right below that says testing hypothesis regarding a population mean p-value approach with a TI-83 or 84 calculator. So we need to also check to make sure that we can perform the test. This time we're going to check to see that we have a simple random sample and that the population is normally distributed or our sample size is large, which we say is greater than or equal to 30. Next thing is determining your null and alternative hypotheses, figuring out your alpha value, which is usually given to you. Then to find our p-value, we're going to go to Stats, Test, and go to T-Test. If raw data is given, we're going to highlight Data, put your values into L1, and frequency needs to be set to 1. If summary statistics are given, highlight Stats. Mu naught is going to be the value of the mean stated in the null hypothesis. You need to state the direction for the alternative hypothesis, and then calculate, select Enter. Then we're going to get our T statistic, which is our test statistic, and our P, which is our p-value. If the p-value is less than alpha, we reject the null hypothesis, and then we're going to state our conclusion. The example says, in 1990, the mean height of women 20 years of age or older was 63.7 inches based on data obtained from the CDCI and the Prevention's Advanced Data Report number 347. Suppose that a random sample of 45 women who are 20 years of age or older today results in a mean height of 63.9 inches with a standard deviation of 0.5 inches. So first part A says, is all the criteria met in order to perform the test? Since we're talking about the average height for women or the mean height for women, we only have 2 things to check. This has to be a simple random sample, which it is. And second, our sample size, which is n, and our sample is 45 women, has to be greater than or equal to 30, which it is. Part B says state the appropriate null and alternative hypotheses to assess whether women are taller today. So our null and our alternative. Since we are talking about average or mean, we're going to go ahead and put mu. For our null, it's always equals to. And that value that we have is what the population is. And that population that we have is 63.7 inches. And taller today would mean that it would be greater than that 63.7. Part C says use the p-value approach to test the claim that women are taller today. So from here, we need to enter in our data into the calculator. We are going to go from stat to test, go down to t-test, select enter. We are dealing with statistics on this one, so go to stats. Mu naught for this problem is 63.7. X bar is 63.9. S is 0.5. And our sample size is 45. Our alternative hypothesis is greater than. And then scroll down to calculate, hit enter. And we get T, which is our test statistic, and P, which is our p-value. From the calculator, we get the p-value is equal to 0.0051, which is less than alpha. Alpha is equal to 0.05, and this means that we are going to reject H naught. So in conclusion, there is sufficient evidence at the alpha equals 0.05 level of significance to conclude that women are taller than in 1990. The next example that we have, we will go ahead and circle, and we will look at that one together in class. The next example says, do students who learn English as well as another language simultaneously score worse on the SAT critical reading exam than the general population of test takers? The mean score among all test takers of the SAT critical reading exam is 501. A random sample of 100 test takers who learn English as well as another language simultaneously had a mean SAT critical reading score of 485 with a standard deviation of 116. Do these results suggest that students who learn English as well as another language simultaneously score worse on the SAT critical reading exam? First thing, part A, says to state the appropriate null and alternative hypotheses. Since we're talking about the average reading exam score, our parameter is going to be mu equals for our null, and that value that we have it equal to is 501. And we're asking about, do they score less than or worse on it? So that'd be less than 501. Part B says to verify that the requirements to perform the test using the t-distribution are satisfied. So yes, this is a simple random sample, and our sample is of 100 students, which is greater than or equal to 30. So we are able to perform our test. Part C says use the p-value approach at the alpha equals 0.1 level of significance to test the hypothesis in part A. On your calculator, you're going to go stat to test, down to t-test, select enter. For this problem, we have stats. Mu naught is going to be equal to 501. X bar is equal to 485. Our standard deviation is equal to 116. And our sample size is 100. Our alternative hypothesis is less than. Scroll down to calculate, hit enter. And again, you get T, which is your test statistic, and P, which is your p-value. So from the calculator, we get a p-value equals 0.0855, which is less than alpha, equals 0.10. And this means that we are going to reject H naught. Part D says to write a conclusion based upon your results in Part C. So in conclusion, there is sufficient evidence at the alpha equals 0.10 level of significance to conclude that students who learn English as well as another language simultaneously scored worse on the SAT critical reading exam. The next example says, data collected on earthquakes list earthquake depths And the summary statistics are N is 600, X bar is 5.82, and S is 4.93. Use a 0.01 significance level to test the claim of a seismologist that these earthquakes are from a population with a mean equal to 5 kilometers. Assume that the criteria has been met to perform the test. So we need to go ahead and write down our null and our alternative. And since we're talking about the mean depth, we're going to go ahead and put mu in. And the mean for our null is always going to be equal to. And that depth that we have is 5.00. And that they think it's different, so not equal to 5.00. So from our calculator, we get a p-value equal to, it's 5.24 times 10 to the negative fifth, which if we rewrite this and move the decimal place 5 times to the left, we have 0.0000524, which is going to round to 0.0001, which is less than alpha equals 0.01. And this means we're going to reject H naught. So in conclusion, we would say there is sufficient evidence at the alpha equals 0.01 level of significance to conclude that the mean depth of earthquakes is different than 5 kilometers. Next thing that we have is practical significance. This refers to the idea that while small differences between the statistic and parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or to be considered important. Large sample sizes can lead to results that are statistically significant, while the difference between the statistic and the parameter in the null hypothesis is not enough to be considered practically significant. We have another example on the next page that says Michael enrolls in a course that is designed to increase reading speed. Prior to enrolling in the class, Michael read 198 words per minute. The following data represents the word per minute read for 10 different passages read after the course. Part A says because the sample is small, what must be done to determine if the sample comes from a population that is normally distributed. So this was discussed in chapter 6. And so there's 3 things that we need to check. First thing would be that our histogram is roughly bell-shaped. The next thing that we had to check was that we had at most 1 outlier. And then the third thing that we had was our normal quantile plot. Has to be approximately a straight line. So approximately straight line. And this is back in section 6.4. So if you don't remember that, maybe go back and review that. Part B asks, was the class effective? Use the alpha equals 0.10 level of significance. So in order to do this test, we need to set up our null and our alternative. Since we're talking about the average words per minute read, our parameter is going to be mu, an equal sign for our null. To figure out the value that we have for our mean, we need to look at the words per minute that Michael read prior to enrolling in this course, and that was at 198 words per minute. And since taking this class, we would hope that his words per minute has improved and it's effective, meaning that he's reading at a faster rate. So we have 198 greater than that. So in order to do this problem, we have to take a moment to enter in all of our numbers into L1. And then we also need to run our test. On your calculator, we're going to go to Stat, Edit, and enter in all the numbers into L1. And then we are going to go Stat to Test, down to T-Test, select Enter, And this time we have data, since we put our raw data into L1. So mu naught is equal to 198. Our list is in L1. Frequency needs to be set to 1, and our alternative is going to be greater than mu naught. Go down to calculate, select enter, and you get your p-value and your test statistic. So from the calculator, we get a p-value equal to 0.0033, and this is less than alpha, which is equal to 0.10. This means that we are going to reject H naught. From here, we need to write our conclusion. So, in conclusion, there is sufficient evidence at the alpha equals 0.10 level of significance to conclude that the class is effective and his reading speed has increased because of the class.